Okay, so get ready because we're about to dive into one of those questions that's like deceptively simple, you know? It's one of those questions that everyone kind of asks as a kid, but then when you actually start to think about it, it's like, whoa, this gets really deep really fast.
It really does.
You guys sent us in physicist Sean Carroll's paper, and it's all about whether math is actually real.
Yeah.
Like,
Yeah.
out there in the universe, if there were no humans to think about it, would 2 plus 2 still equal 4?
Mm.
It's a total brain twister, and that's what we're tackling in this deep dive.
Absolutely. And I think Carol's perspective is one of those that really challenges you to think differently about, like, the connection between what's going on inside our own minds and what's actually happening out there in the universe. So true. So we're really going to get into it. We're diving deep into his paper, Realism, and like his whole jam is that he's coming at this from a physics perspective.
Right.
And he's saying that it's the physical universe that's truly real. Okay, fine, but then where does that leave something like math?
Right. Because, I mean, you use math every day. It feels pretty real when you're trying to, like you said, split a check or figure out how much longer you have to drive.
Exactly.
So Carroll's view kind of boils down to this idea called Humism,
Mm-hmm.
which sounds like a really big, scary word, but it's actually a pretty simple idea once you kind of unpack it.
Okay.
It basically means that, like, the laws of physics,
Hmm.
right? They're not some kind of separate, like, rule book out there that's dictating how things work.
Okay.
It's more like they're our way of describing the patterns that we observe. So it's like the laws of physics are less like rules and more like, I don't know, descriptions maybe.
Exactly. It's like saying what goes up must come down is our way of like summarizing how consistently gravity works.
Okay, I'm with you so far.
Okay.
But how does Carroll take this humanism thing and apply it to math? Because like, that still feels like a whole other level of realness to me.
Right. So he uses this really interesting analogy where he asks us to imagine aliens, out there in the vastness of space, and they're counting their spaceships. Now, they might not use the same symbols that we use.
Right, they might not have, like, Arabic numerals like we do.
Exactly. Maybe they use like, I don't know, squiggles or sonic vibrations or something completely different. But the point is, they'd still arrive at the same mathematical truths that we do. So like 2 spaceships plus 2 spaceships, it's still going to equal 4 spaceships, even if they represent it in a totally different way.
Okay, I like that. That's a good way to visualize it.
Yeah.
So are you saying that, like, the specific symbols and equations we use in math, they're almost beside the point? It's more about, like, the underlying reality that math is trying to get at.
Exactly. Yeah, it's about the underlying reality. So it suggests that, like, at its core, math is more about the underlying reality that it's describing than it is about, like, some separate abstract realm of numbers that exists independently of us.
So it's also like saying math is a language that we've developed to understand the universe's structure.
Mm-hmm.
Kind of like how, like, we use language to communicate with each other.
Yeah.
But there are different languages that can express those same ideas.
That's a great way to think about it. Just like language helps us understand the world around us and communicate our thoughts, math helps us understand the universe and communicate its patterns.
I like that a lot.
Yeah.
Okay, that's really interesting. But here's where it gets even more interesting for me, at least.
Right.
Like when people talk about the unreasonable effectiveness of math.
Right.
Have you heard that phrase?
Oh, yeah.
It's like we see math constantly, like, explaining things in the universe,
Yeah.
especially when you start talking about physics.
Uh-huh.
Like, it's mind-blowing how math can describe the way planets orbit stars or, like, how particles act at the quantum level.
Yeah.
It's all incredibly mathematical. So that's got to count for something, right?
Cool.
It's not just a tool, right?
Yeah.
Like, it's got to be more than just a description.
Yeah, that's a really good point. You're actually tapping into something that a lot of physicists and philosophers have really wrestled with.
Right.
So Carroll actually addresses this unreasonable effectiveness argument directly, and he says, yeah, the standard model of particle physics, which is like our best current description of like the fundamental particles of the universe,
Right.
it's incredibly mathematical.
It's like mind-blowingly accurate.
It is. It's amazingly successful at predicting how particles are going to interact. But here's the thing. Even the standard model, as powerful and as accurate as it is, it's still just a model. It's not reality itself.
So it's like the difference between like having a really good map of a city
Yes,
and actually walking down those streets.
exactly.
Like the map can be super accurate,
Uh-huh.
but it's not the same as the actual experience.
And that's what Carroll's saying about the standard model. Like
Okay.
it's a representation.
Gotcha.
And that's really important because it means that maybe someday we'll come up with a better model, a model that uses a completely different kind of math to understand the universe.
Okay, so you're saying that even if in the future physicists come up with like some crazy advanced math that we can't even conceive of right now,
Yeah.
it doesn't mean that our current models were wrong.
Not necessarily. It just means that our tools for understanding the universe have evolved,
Hmm.
right? It's like Newtonian physics, it's still really useful for understanding everyday stuff, like
Yeah.
how buildings stand up.
Right.
But then Einstein came along with general relativity, and that like totally revolutionized our understanding of gravity and the universe at large.
So it's like those old maps from like way back when. Like they might have had some inaccuracies,
Mm.
but they were still useful for navigating the world as people understood it at the time.
Right, exactly. And speaking of navigating uncharted territory, let's talk about abstract math because that's a whole other
Oh, yeah, that's what I was going to say.
can of worms.
Because there are like entire branches of math that seem completely disconnected from like the physical world that we experience as humans.
Totally.
Like what about concepts like infinity?
Yes.
Does the concept of infinity even exist if we never actually encounter it out there in the universe?
That is a fantastic question, and it's something that Carroll actually addresses in his paper.
Okay.
He says there's a really important distinction between the kind of math that we use to describe like the physical world around us.
So like counting apples or like measuring distances.
Exactly like the stuff that we experience every day,
No.
versus the kind of math that deals with more abstract concepts that are extrapolations of those rules that we observe.
Okay.
And he's more willing to grant that first kind of math, the math that's like directly tied to physical reality, a status of realness.
Okay, so some math is more real than other math.
It's more about how grounded it is in the physical world that we observe.
Give me an example of like one of those abstract mathematical concepts.
Okay, so a really good example that he uses is something called the continuum hypothesis.
Okay, the continuum hypothesis.
It's a little bit of a brain teaser.
Lay it on me.
Okay, so basically the continuum hypothesis is dealing with the idea of infinity.
Okay.
And that we can have these like infinite sets of numbers, but some infinities are in a way bigger than others.
Okay, like how there are infinitely many numbers between the numbers 1 and 2,
Exactly.
even though like 1 and 2 themselves are just like regular finite numbers.
Yeah, and the continuum hypothesis tries to figure out if there's a size of infinity that exists between the infinity of all whole numbers and the infinity of all real numbers.
Okay.
And here's where it gets really wild. It turns out you can't actually prove if the continuum hypothesis is true or false using like our standard mathematical rules.
Wait, are you saying there are unanswerable questions in math?
It seems that way.
I thought it was all about logic and finding like a concrete answer.
Well, it turns out that math is a lot more mysterious and strange than we sometimes give it credit for.
Okay, so then how does Carroll explain that? Like, how do you reconcile that?
Well, for Carroll, this like unanswerable question about the continuum hypothesis suggests that maybe these very abstract mathematical concepts, like the specific sizes of infinity, maybe they don't actually have a direct counterpart in the physical universe.
So it's like their truth, or whether they're even true at all, is kind of beside the point when we're talking about describing like physical reality.
Exactly. It's like if you had a perfect map of the United States, but then you tried to use it to navigate through the Amazon rainforest,
Okay.
like the map itself might be internally consistent,
Right.
but it's not going to be very helpful in that completely different context.
Okay. That's actually a really helpful analogy.
And that's kind of how Carroll sees these very abstract mathematical concepts.
Okay, so we got some math that seems to be very closely tied to the physical world. And then we've got this other realm of math that's more abstract and might even have unanswerable questions.
Yeah, and then Carroll takes us into another really fascinating aspect of math, which is the idea of consistency.
Okay.
And what that means is that within a specific mathematical system, you shouldn't be able to arrive at contradictions.
Like you shouldn't be able to prove that 2 + 2 = both 4 and 5 at the same time.
Exactly. Math has to be consistent. And this is where things get really interesting because some mathematicians and philosophers have argued that if math wasn't somehow fundamentally real at its core,
Okay.
then we would always be running the risk of like stumbling upon some kind of logical contradiction that would completely shatter our understanding of how math works.
Whoa, okay. So you're saying there are some people out there who think that, like, if we just keep digging deeper into math, we might eventually find, like, a glitch in the matrix.
Yeah, like some fatal flaw, some
Yeah.
fundamental contradiction that just like throws everything we thought we knew out the window.
Exactly.
Exactly. That's the fear that some people have. But Carroll pushes back on that a little bit.
Okay.
He says that, like, even if a mathematical theory seems perfectly consistent, like on paper, it seems to work out internally.
Hmm.
The real test, the real way we know if it's actually telling us something meaningful about the universe is whether it has what's called a model,
Okay.
which is basically a way of representing itself in a way that aligns with the physical world.
So it's not enough for the math to just be, like, internally consistent. It has to actually, like, match up with what we
Oh,
observe out
sure.
there in reality.
Exactly. The universe gets the final say.
Okay.
If our math doesn't actually line up with the way reality works, then it's our mathematical system that needs an update, not reality itself.
Wow. That's kind of a humbling thought in a way.
Yeah.
Like, we like to think of math as this, like, perfect system.
Right, like we've got it all figured out.
Yeah, but it might just be, like, a limited perspective.
It might be a piece of the puzzle, but it's not necessarily the whole picture. And that's really what Carroll is getting at, I think.
So if I'm understanding Carroll correctly, he's saying that math is like our way of describing the universe,
Uh-huh.
but it doesn't necessarily, like, dictate how the universe behaves.
Yeah.
It's a tool.
Yeah.
It's a really, really powerful tool.
It's a tool that's allowed us to understand the universe in ways that, like, we could never have imagined. But it's still a tool. It's not the universe itself.
I like that a lot.
It's a perspective that I think can be really helpful because it allows us to be a little bit more open-minded about the possibility that maybe there are other ways of understanding the universe.
Right. Are there other tools that
Mm.
we could be using, other systems of thought, other, like, yeah.
Exactly. And maybe there are limits to what our current mathematical systems can even describe.
Okay, so, like, what if we discovered a completely different kind of universe out there
Yeah.
with its own set of rules and laws?
Right. Would our math even work there?
Yeah, would we need to, like, invent a whole new system to even begin to wrap our heads around it?
And that question, I think, is like the perfect place to leave this conversation because it really highlights how much our understanding of reality is shaped by the tools that we use to observe it.
That's a mind-blowing thought to end on. I think I need to go, like, for a walk and let all of this marinate a little bit.
It's a lot to take in.
It really is. But thank you so much.
Yeah.
This has been, like, an incredible deep dive. I feel like my brain has expanded.
I'm glad to hear it. It's always fun to dive into these big questions.
And to everyone listening, keep those brain-bending questions coming because you never know what kind of, like, fascinating rabbit holes will go down next.
Absolutely.
Until next time, happy diving.